So the plan for today, I'm going to hand back the exam to Ian, so I'll leave plenty of time for that. So I have most of you are pretty well. Lots of people got 100. I'll show you the distribution. I'm pleased. But first, we want to finish the chapter we're on, which is chapter 11, and then move on to chapter 12. I don't know if I'll finish chapter 12 today, but if I don't, what I will do instead is finish it next time. There won't be very much, and then I'll just leave the rest of the time for review questions. So next time I'll leave as much time as I can for review questions. They'll be coming and ask me about topics and things. I really don't want to try to cover the whole course in an hour, then focus me on topics. I can certainly talk about those and do it thoroughly. And more than willing to do that. So that's the plan. So hopefully you'll have lots to ask me next time. The other thing is I'm going to post some questions on the last couple of chapters. I have an assignment as homework, so I decided the homework experiment was a failure. So what I'm going to do is I'm going to calculate grades with the homework in there. Then I'm going to calculate it with an out. And I'll give you the highest you get either way. Okay? So I don't want to penalize the people that worked hard on it, but there was too much variance in it to let it affect anyone negatively. And so I will look closely. If you didn't do any homework, I'm not going to probably adjust it. But if it looks like you just got, bad draws and things, I'll make some allowance. I'm going to make, if I see a string of zeros, I may not be quite as generous there. But I'm not going to let anyone get hurt by the homework, is what I'm trying to say. I don't think it worked out the way. And then some of the exam questions will, of course, be drawn from the homework I assign, or the questions. And the questions I put up, it's probably tomorrow, maybe the next day. Will just be things we covered in class, just like the last homeworks have been. So you can go through them, dig it out. Your job is sort of to figure out how to answer these questions. And you can be pretty sure they'll be on, some of them will be on the exam if you know how to answer them, so you'll get a step ahead. Anyway, let's get going on chapter 11. So the last topic in this introductory chapter on growth, I guess it's the second one. We had the facts of growth and now the model of growth. But what we haven't really talked about yet is human capital. And it seems like that ought to be important, that countries with different levels of education and skills and other sorts of things might have different levels of productivity. And so the question is, well, how do we get that human capital into our model? Because if you look at the last 200 years, and these are just from some statistics from the book, at the beginning of the Industrial Revolution, 30% of the population in developed countries basically could read.
You can hear us, so sorry.
Sorry. So 30% could read. Today it's 95. So there's been a huge increase in human capital. Virtually 100% of people get schooling these days in developed countries. And so there's been a huge, substantial increase in human capital. We'd like to be able to figure out what impact that has on productivity. And is there some way to do that? So what we're going to do is we're just going to take the basic model. Before it was Y, it was a function of capital and labor. Remember how that worked? Now we're just going to change it to say, well, Y is some function of capital, labor, and human capital. So this H will be human capital. So that's what's going to be do here. And so for a given population and a given amount of plants and equipment, smarter populations have more output. With more human capital. It doesn't have to be education, it's just, knowledge that helps you in the productive process. It can be the institutions as well. Now again, we're going to assume constant returns to scale. So we can say y is some function of k over n, 1, and h over n. And then we're just going to write this as a little f of k over n and h over n. So this is y over n on this side, sorry. Notice the different f here. We just dropped that. Different function.
Is that a one?
Yes,
One, okay.
because we divided the whole thing by n.
Okay.
Because it's constant return, we can just bring it right inside here. That's what basically CRS tells us. We divide both sides by something, we can bring it inside the function. So there's really not that much new here. It's telling us that the standard of living still depends upon capital accumulation, but it also depends upon the accumulation of human capital. So how does this change our results so far about growth and savings and all that stuff? First is that all the claims we've made about capital accumulation are still valid. For instance, an increase in the savings rate causes y over n to go up to a new steady state, just like we said before. So that wouldn't change at all just because we added human capital. Oops. The results for k over n that we've derived extend to h over n. As we save more and invest in human capital, education, job training, that job training can be on the job or off. That's sort of money we're setting aside to invest, except we're investing in people, so we're saving in a different way. It's turning into a different kind of investment. You can sort of think of that as we save and invest more. And invest in human capital. So that h over n goes up. That will also cause y over n to increase to a new steady state. We're not going to write down a graphical model like we did before. We've already done this, but it's a straightforward extension, same sort of thing. So what we've learned is the standard of living, y over n, depends upon how much we save, that's S, and how much is spent on education. Education is sort of broadly construed there. And the last thing we'll say is that studies indicate that K over N and H over N are roughly equally important. In explaining the standard of living, in determining the standard of living. And I'm going to let you catch up.
Number 3 depends on saving, and what's the second one?
Oh, how much is spent on education? Different kinds of savings. Say it, yes.
The spending on education is the same as spending on human capital.
Yes. Education, as I said, really broadly defined as all that kind of spending that helps you be more productive from a mental sort of, even on the job training would count as sort of education. You're taking resources you can be spending in other ways, and you're investing in people. And that's, what does that say? Studies indicate K over N and H over N are roughly equally important in determining the standard of living. Turns out it's really hard to measure how much human capital there is in a society. You can look at average levels of education and things like that. It's actually not that easy to figure out. It's actually hard to measure capital too. We don't have a very good measure of the capital stock. Pretty good measure of investment, but the stock of capital is hard to measure. So you got really bad data. So maybe roughly equal, but in a qualified sense, it's not that solid an estimate in the back end. Okay, now the last topic here is that the book talks about is endogenous growth. And I am not going to spend very much time on it because it's mostly a setup for the next chapter. So what we've shown so far, we've shown that when H over N or K over N go up alone, one or the other, Y over N, the standard of living goes up, but there's no permanent change in the growth rate. You get a temporary burst up to a higher level and you grow just like you grew before. The same growth rate. So it doesn't change the growth rate. Y over N stabilizes at a higher value. And that's just, we used that diagram last time. We showed that Y over N jumps up when K over N goes up, so we just move to the right on the bottom axis and so on. But the claim that an increase in human capital can't cause permanent growth has been challenged. So the claim that H over N does not cause a permanent increase in growth has been challenged. The big names are Robert Lucas and Paul Romer. And we're still fighting about whether they're right about this or not. Jury's still out on these models, I think it's fair to say. But basically, they ask, what if the increase in human capital increases technological progress. So they ask, what if an increase in human capital causes an increase in technological progress? Couldn't that permanently change the growth rate in a society? And the answer we're going to look at next in the next chapter is, yeah, it could. And so if you had more education leading to a more innovative, more R&D, more of that sort of stuff, then you're going to see, you'll see more technological progress, and that'll increase our growth rate. So now we want to look at how technological progress impacts growth. So that's chapter 11, or chapter 12. So that leads to chapter 12. The last one. We're going to add two things to this model that can affect the growth rate in the economy, and that's population growth and technological progress. But it's just technological progress that's going to raise the standard of living. You get more people for the same capital and the same technological progress, that's not good. So we're going to add population growth and technological progress. Let's see what happens. Now by this we mean better products, more variety, new products, all sorts of things. So we're going to think of technological progress, broadly defined, and we're just going to represent all of that as an increase in output. We'll just think of better stuff as being like having more for your money, that's more output. So we'll just model technological progress as an increase in output. So this could mean that output goes up for a given K and N. So and H even, if you have it. So with technological progress, you're going to get more output for a given level of capital and labor. Yes?
Oh, that's not bad.
So the same as said, that means better products. New products. Be more variety. So it figures out how to make a different color something, or I don't know. All these different variations, you might not have that technology progress. So we're just going to represent as an increase in output. So we're going to think of all those things. If you think of output as a set of services, never mind. We'll just, the book makes an argument about why you can do this, but maybe we'll think of it as this. Technological progress is an increase in output for a given level of K and N. And then you can make an argument that you're capturing these kind of effects with that model. Maybe we're thinking of that. So we'll do it this way. We'll say Y is some function of capital, labor, and this time we'll put technology. Instead of human capital, we'll put technology. And this is technology, state of technology. And all of these have a positive effect. When capital goes up, labor goes up, or technological progress increases, we get an increase in output. Nothing new there. It's convenient use a restrictive form, so we're going to restrict this a little bit. So we're going to write y is some function of capital and the product of A and N. So we're going to use a specific form of the production function. Yes? What was A? A is the state of capital production. AN, and we'll explain why in a moment, is called effective labor. What this production function says, two things. In this form, it tells you that technological progress leads to a reduced N to produce the same level of output. So we're saying that
Give you time to catch up by March 9.
So we're saying that if you hold y and k constant, and A goes up, you have to drop in, keep y constant. So in this form, you get that technology displaces labor for the same standard of living, essentially. So it has that effect built in. And also it has that technological progress. And by that, we just mean an increase in A. Causes output to go up with the same N. So if you hold N constant, increase A, of course, output goes up. And we're assuming diminishing returns and all the same things we've always assumed about this. So that's all that stuff built in. Now, we're going to still assume constant returns to scale. So we can say that y over AN, output per effective worker, is equal to F of K over AN, and 1. And just like before, we're just going to write that more conveniently as this. So that's what determines output per effective worker in this model. So what have we done? We added A to the production function, so let's multiply A and N together, then we divided by A and N. And it took us about 10 minutes to do that. That's all we're doing. And A is technology. So this is just the basic standard all production function. Here's our input. Here's the output. And it has diminishing returns. Flattening out is diminishing returns. You get less and less output per person, effective person. All right, now we're just going to do exactly what we did in the last chapter, with one small twist along the way. So we really just divided by A on both sides. Kind of all relative cost. This is effective labor, because if you fix the number of people and increase A, you get more output, they're more effective, they're more productive. And so A times the number of people, just the number of people doesn't tell you how smart and productive they are. But AN gives you the effectiveness of that number of people. And so it's just trying to capture that kind of effect. And this is just showing diminishing returns. Okay, let's find the equilibrium. As before being chapter 11, investment equals savings equals SY. So we're modeling the savings function is just equal to S times Y. Then we can say, okay, that means that I over AN equals S over AN equals SY. We're just saying, when government spending equals taxes, like we've assumed, and there's no foreign sector, savings equals investments in equilibrium, and this is the way savings is determined. Then we just divide by here. We know what this is, though. That's this thing. So this term here is F of Y over N. So what we have is that investment per effective person equals savings. So what the equation we're going to need is just this. I over AN equals S F of K over A. So this is investment equals savings. And then we asked what level of investment is needed to keep. In the last chapter, it was K over N. Here, it'll be K over A. So, so maybe the K over AN constant. The way we did this in the last chapter is we said it must be that. So the last chapter, we said, well, it means that investment equals depreciation. This was last chapter, no A. So the last chapter, that was a condition. And we said, oh, this is just S F of K over N equals delta K over N. And then we drew this diagram where we had delta K over N. This was K over N. Y over N was up here. Then we had the savings function and the output function. This was S F of K over N. And this was F of K over N. And then the steady state is that point right there in this slow down. So this is just, we're going fast because we did this twice or 3 times already. This is just reviewing what we did in the last chapter. So what we said is what we need for an equilibrium, for a steady state, is we need that investment is exactly equal to depreciation. The new stuff coming in is equal to the stuff that gets destroyed. Then capital will stay constant. So, okay, investment is savings. Savings equals investment, so this must be the condition. Then we do a graph of it. This is where S F of K equals delta K over N. So that's what we call K star over N. And then we came up to here, and that's the production function. We found Y star over N. We want to do the same thing, but with technological progress in the model. So here, it's a bit more complicated. So let's just define some things, write down the answer, and then try to understand it. Okay, so I'm just going to forge ahead, knowing you're not quite sure where this is headed yet. And then hopefully at the end you'll see we're doing something absolutely analogous to this. This term needs to be different now when we have technological progress in population growth. That's what's going to be different. So we're going to let delta, again, be the depreciation rate, so nothing new there. G of A is going to be the growth of technological progress. That's the growth rate of A. It's the percentage change in A over time. It's how much it's grown. And G of N is going to be the population growth rate. Now, let's see, how do I want to do this? We want to keep K over AN. We want K over AN constant. So K needs to increase for 3 reasons. Let's see if I can try to do this differently in the book and maybe make it a little clearer than what's going on in there. One, depreciation. Right? We need to increase K to compensate for depreciation. That's just going to be delta K like before. But 2, growth of A. If A is going up by 5%, this has to go up by 5%. It's not going to stay constant. Right? And 3, the growth of N. So what we're going to have this time is that the investment that we need is delta K plus GA plus GN times K. This is the growth of AN, the growth of effective labor. That's this part. Percentage change in X times Y is percentage change in X plus percentage change in Y. It's like you take a log and prove that. It's a sum. Anyway, this is the growth rate of AN. So this is just the 3 effects. 1, 2. Because you want to keep K over, that will keep K over AN constant. You need to increase K by the depreciation rate, by the growth in A, by the growth in N. If this was 2% and this was 3%, capital would have to grow by, this is then growing by 5%, so this would have to grow by 5%, G of A plus G of N times K. To stay constant. All right, then we're almost there. So now we can do just what we did before. We can say, okay, well then I over A n equals delta K over A n plus G of A plus G of N times K over A n. You can actually group those two terms because they're the same thing. Again, this is just S, F, of K over A n. We showed that earlier. So what this tells us then is that S, F of K over A n. This is the steady state condition, is delta plus GA plus GN times K over. And now it's just a matter of playing with that model. That's the model. We just need to, this is just what it was before, except we just had delta. G of A and GN were 0, and we made A 1 because we didn't need it. So in the last chapter, GA and GN were 0, the N was fixed. There was no growth in technology at all. So we just made A equal to 1 because it's easiest to just make it 1 instead of something else. So the last chapter is just a special case of this model where those three things are true. We could have the A in there, it wouldn't change anything. So let's draw this one graphically. K over A, and we're going to find the steady state again. And like before, this is just a straight line. Out of the origin. So one line is delta plus GA plus GN times K. Right? That's this side right here. We graph this. Because of diminishing returns, we know that has eventually crosses that line because it gets flatter and flatter and flatter, and the line goes on forever. So it's got to cross it somewhere. So this line looks like this: S, F, K over A n. And then this then is the steady state: K over A n star. And then we add the production function. This is a fraction between 0 and 1. It's a savings rate out of income. We add the production function f of k over a n. And that gives us, this isn't quite the standard of living, but it gives us a steady state of output for effective work. We're actually going to be interested in y over n. And we'll come to that soon. What would happen down here? Suppose you were down at this K over A. What would this point here do? This is investment, essentially. So that's the addition to capital. And these are essentially the loss. It's depreciation and population and technology growth that make you have to have more output. So at this point, you would have that the K over AN would be going up. Let me use the book's notation here. This is point D in the book, and this is point C. So investment, which is point C, the new capital is greater than depreciation, the needs due to N going up and K going up. So you're investing more than you need to cover depreciation, population, and this is point D. So this is what you need. So the new capital is greater than what is needed to keep it constant. If that's true, it must be increasing. You're investing more than you need to keep it constant. On the other side, you move in this direction, so this is an equilibrium, it's a steady state. So what does it tell us? So it says Y grows at the same rate as A N. Right, if that's going to stay constant, Y has to grow at exactly the same rate as A over N. So what we know now is that the growth rate of output is GA plus GN. And note that it's independent of the savings rate. So the growth rate of this economy is going to be that. What we're interested in is the standard of living. Let's see if we can figure out what that's going to be. Let's see, what's the best way to do this? The growth in Y over N is the growth in Y minus the growth in N. The growth of X times Y is the growth in X plus the growth in Y. The growth of X over Y is the growth in X minus the growth. Those are just results from math. You get it by taking logs. I'm not going to do the proof. It's really easy, but it relies on something you probably don't. Anyway, those are true facts. And you can prove it mathematically if it has to be the case. So the growth in Y over N is the growth in Y minus the growth in N. Right? So the growth in Y over N, which is what we're interested in, has to be, we know what this is, it's G of A plus G of N. That's the only way this can be constant if Y is growing the same way as those are. And this is G of N. So the growth in the standard of living is equal to the rate of technological progress in this model. So the standard of living grows faster or slower depending upon your rate of technological progress. That's where the human capital from the last chapter comes in. If human capital increases, the rate of technological progress, not the level, the rate that technological progress is growing, and that's going to cause an increase in the growth of the standard of living. So we finally have something that will change this over time. In the last model, G of A was 0, so the growth of this was 0. That's in the long run, because you're at the steady state, by the way. If we go straight through, I could probably finish in another 15 minutes and hand the exam back and we'll all be out of here. Can we do what we do next time? Why don't I do that? Is that okay? If anyone's dying for once, I won't get offended if you jump up and have to go.
So next class will be reviewing.
As I explained already. So basically, just some cleanup stuff at the end. What are the determinants of technological progress? That seems to be the key, at least according to this model. You look at the data, it's not occasional large discoveries, you know, it's somebody in the garage discovering something you just can't believe. It's so cool. What it seems to depend mostly on is research and development spending. In most developed countries, that's about 2 to 3% of GDP. You look at total R&D out there. So it's sort of that sustained research and development effort. You know, it might matter whether it's basic research or directed research and all that other sorts of stuff, but it seems to come down to that. So R&D is fundamentally ideas. That must be turned to profit. So, the level of R&D spending, it seems to have a lot to do with technological progress. depends upon two things. One, the fertility of research, which I thought was a strange word, I'm using the books. This is just how well R&D spending translates to technological progress. So that's just how well R&D translates into new products, into useful ideas, new ideas and products, let's say. If you're getting a new useful drug for every $1 billion instead of every $2 billion, that's more fertile. And so how fertile that research is. You'll do more. The other thing is what you call appropriability. I've never actually seen that word before. Appropriate, that's where it comes from. Appropriability. This is the extent to which a firm benefits from its own R&D. Now, patents protect that mostly. So without a patent, your idea is not easy to appropriate by others. They can't steal it and take it. But often when things are difficult to patent or difficult to you can do a derivative product that's just easy to copy but not quite the same thing, it's often best to be the second mover. Because if you're the second mover, you let them do all the R&D, then you can just come in and do some slightly different thing that's legal and do your own product, and you've skipped all the R&D, but you've benefited from the ideas. In those kinds of cases, you're going to have much less profit. And so this is really the extent to which your ideas can be protected in the world marketplace. If some other country could just come in and copy it without any worry, then you've got a problem too with certain kinds of ideas. Okay, finally, before the conclusions, let's take a quick look at the data. So is it true that y over n grows at rate GA? Another reason the standard of living could grow, you could start at this standard of living. You're a country with not enough capital. So over time, capital accumulation could cause the standard of living to rise. So the alternative is capital accumulation toward the steady state. You know what I mean? So from here to here raises the standard of living. So that's one reason why the standard of living might have risen in some countries, is because they're below their steady state level of capital and moving toward it. The other reason it might be, though, is because of G&A. We're trying to say, well, which one of those is it? So if you look at the data for France, Japan, the UK, and the US, so this is data from 85 through 09 for France, Japan, UK, US, average. This is the growth of y over n, and this is the growth of a. It's g of a. 1.9, 1.8, 2.1, 1.9, 1.6, 2.1, 1.6, 1.3, 1.7, average. So two conclusions. It's only going to take 15 minutes. We're almost there. Hang in there. So we can say a couple of things. Growth since 85 seems mostly due to technological progress rather than top-down accumulation. Overall, it's not a bad fit. Quite a bit of variation individually. Convergence in growth rates. So we talked about the data before, and said over time there's this convergence in growth rates. Seems to be from technological progress as well. France. Who's the slowest growing country? US, Thailand. Wait a minute, something's wrong here. Excuse me, country with the least technological progress. Sorry. Is the US. The other countries have higher rates of technological progress, so they should have higher growth rates. And so what we're saying is that France, Japan, and the UK were all behind the US in '85, but they had faster rates of technological progress, which should cause them to catch up, according to the model. And so we try to say, what's convergence over time due to, then it's mostly seems to be technological progress. Now, this is for developed countries. The last qualifier you want to make here is that for a lot of poor countries, they really are in a really low capital state, and they're way below their long-run steady state. And so growth in the standard of living of poor countries is often mostly due to capital accumulation. But in wealthy countries, it seems to be mostly due to technological progress and skill. So, hope you got the last one. Because I'm too tired to read. Okay, so the last point on this. Let me put the scores down and talk a little bit and then hand them back. I should have done this on an overhead or something. This will take me a minute, sorry. I just want to show you the distribution. almost there. Some technological progress. Isn't it? Yep, so I have to go lower. Unfortunately. Okay. 6 there. 1 there. 1 there. 8 here. 6. 2. 3. 1. 6. 2, 3. So there it is. Let's see. N equals 82, but I suspect some of these people are just gone. They're not really part of the distribution, we just don't know it yet. So, we'll see. The min was 0, max was 100. The mean was 67, rounded. And the median was 75. So that's the half above, half below point. That's a pretty good median. What's happened is it's really skewed downward. There's a lot of people, when they blew it big. But they were bounded above by 100. Those kind of people balance, I guess, 6 and 6, but the tail's pulling down the median. But the halfway point's great. That's really good for everything. So I would probably do, I couldn't decide where to put the A, so I'm going to just draw it right through there, because when I average, they'll move around a little bit. It's too many A's, and not enough A minuses if I did it that way. A minuses probably go to there. I don't know, this is just rough. B plus somewhere in there. B somewhere in there. B minuses down there somewhere. C plus. C's in here. C minus is in that range somewhere. Starting about here, I'm really worried about those. Somewhere around there, we're starting with D's. And certainly by here, we're getting into the F sort of a range. So I can't possibly get this one. I've got so many people doing well. That's sort of how I would see it if I had to just grade this test. And those lines are very easy.